right, welcome to dynamic equilibrium. So let's go red, I guess. Equilibrium and dynamic. So the word dynamic means changing, and equilibrium doesn't necessarily mean equal, it just kind of means like a balance. So dynamic equilibrium is a closed system in balance, so it has to be like a closed Erlenmeyer flask with a stopper, because otherwise things could enter in and things could escape, so it has to be closed. Now, these two things are very important. Equilibrium, the rate of the forward reaction will equal the rate of the reverse. So first of all, you're going to see, let's just say A plus B. You're going to see either a double-sided arrow that looks like that, or you're going to see a double-sided arrow that looks like that. So in either case, this is the symbol for equilibrium. And so we call this way the forward reaction. We call this way the reverse reaction. So at equilibrium, the rate or the speed of the forward reaction will be equal to the rate or speed of the reverse. So A plus B forming C is going to happen at the same speed as C breaking down to B and A. So a way that we've found to help remember this is a made-up word called requal. Rates are equal. But concentrations, the amount of each substance, is not equal, but constant. So the amount of A is not going to change as it goes back and forth. B is not going to change. C is not going to change as it goes back and forth, back and forth. By the way, these two things are happening simultaneously. So as this is going this way, this is going this way. So a way to remember this is con. So those are the two takeaways for dynamic equilibrium. Requal, which means the rates are equal, and concentrations or amounts should be constant, not equal. So A plus B doesn't have to be the same as C. They can be different as long as they stay constant. So here's our first picture. It's called phase equilibrium. So right here, you'll notice probably have H2O liquid. And since it's a closed container, you see this is happening, so we have some H2O gas up here. And you'll also notice, so here's our gas, but some of those gas particles are coming back down to become liquid, and some of them are still going back up. So phase equilibrium has to be closed system, like we talked about. The substance is cycling between two phases at a constant temperature. So gee, what's the temperature at which liquid is going to go to gaseous water and gaseous water is going to go to liquid water? Well, that would be 100 degrees Celsius. That would be the boiling point or the condensation point of water. The rate of evaporation would equal the rate of condensation. So maybe you remember from our phase change diagram, I always wrote on these lines a double-sided arrow like this. Liquid. Yes, that's a L. So you always see this, meaning phase equilibrium happening at the freezing point, which is also the melting point. Phase equilibrium happening at the boiling point, which is the same as the condensation point. So that's why I've always written it this way, and maybe now it makes a little bit more sense. So that's something called phase equilibrium. Remember what dynamic equilibrium means. The rate of the forward and the rate of the reverse is equal. See, equal. But the concentrations are constant. So notice how there's a lot more gas than there is liquid. That's going to remain. Solution equilibrium. Remind yourself what a solution is. A solution is a solute and a solvent. And if you remember, the solute goes inside the solvent. That's what a solution is. So a solution equilibrium is saturated, meaning the maximum dissolved solute, again in a closed system at constant temperature. The rate of dissolving solute into solvent is going to be equal to the rate of precipitation, which means solvent getting rid of solute. So here's an example. If you have 3 grams of Kool-Aid that you're adding to an already saturated solution of Kool-Aid, 3 grams is being dissolved. 3 other grams are going to come out because it was already balanced. And if you add 3 in, 3 are going to come out. Are they the same 3 grams? No, but it'll be the same number. Changes in pressure will change solution equilibrium if gases are present. Sorry, it's hard to see that. So remember, pressure is only going to affect the gas phase. The last kind is chemical equilibrium. Just again, kind of in general, forward reaction equals rate of the reverse, con. Yeah, we've got that. And so everything's nice and balanced until it's not, until there's a stress applied. So let's just say everything was nice and balanced and then I added 10 more grams of a substance. Or everything is balanced and then I heated it up. Or we've got gases and I increased the pressure. So we have these stresses. And this is known as Le Chatelier's principle. Don't worry, you won't have to worry about how to pronounce that or say that, but his name is Le Chatelier, probably a dead white guy. So here's Le Chatelier's principle. Applying a stress to a closed system at equilibrium will cause the system to shift in order to regain equilibrium. What do we mean by stresses? Like I was saying, changes in concentration, adding too much, taking some away, increasing temperature, decreasing temperature, pressure for gases only, sorry, you can't see that, and energy or heat. Here's what you need to take away. It's kind of like you're at your dinner table and you just sit down and you're very hungry. So there's not enough on your plate. So if there's not enough, you're going to shift towards. Now, what do I mean by that? We're going to see in a moment, so stay tuned. So if there's not enough food on your plate, you're going to shift the other things on the table towards you to get more. But let's say you've had too much to eat, and so there's too much. So now you've had too much food in your stomach, and people are passing you the plates of extra food. You say, no way, I have too much. So you're going to shift them away. No, I can't possibly have another helping of spaghetti, Grandma. So those are the 2 kind of takeaways you need to know for Le Chatelier's. If there's not enough, the system will shift towards to replace it. If there's too much, the system will shift away to remove some. Those are the takeaways. And so let's apply this using some actual chemistry reactions here. So here's our reaction. You would tell that it's at equilibrium because it would have a double-sided arrow. But then all of a sudden, we have a stress. Everything was balanced, everything was good, and now we have a stress. So over this, NH3, I'm going to write S for stress. I'm going to write an up arrow because it's an increase. Now remember, these brackets mean concentration, the amount, the strength. So everything was balanced and now it's not. So see how I have too much here on the left? Too much, shift away, which means now I'm no longer at equilibrium. I'm going to shift away. When I shift away, everything the reaction arrow points to is going to increase. I will have increase of this. I will have increase of this. I will have increase of this. I am shifting to the right. But what about this? Well, if I'm shifting away, I'm going to decrease the amount of oxygen. And now once this shift has happened, I'll regain a new equilibrium. And that's all the goal is to regain that equilibrium. So that's all you would do. And then a common question would be, if the concentration of NH3 increases, what will happen to the concentration of water? And so you would do this kind of setup, and then you'd see, oh, water goes up. So the concentration would increase. What happened to the concentration of oxygen? It decreased because the reaction shifted to the forward. Okay, let's try another one. Same reaction. This time we're going to increase the concentration of nitrous oxide. And so this is our stress. It's an increase. So now here's where our reaction arrows would be. So if it was at equilibrium, but now it's not. So now with the addition of additional nitrogen 4 oxide. Is it 4? No, it's nitrogen 2 oxide. Anyways, with the addition of this, we're going to shift away. Too much, shift away. Now that we shift to the left, this will go up, this will go up. What about these things? Well, we're shifting away from them, so they will go down. So a common question would be, if nitrogen Roman numeral 2 oxide were to increase in concentration, what would happen to the ammonia? You would say it will also increase. What is the direction of the equilibrium shift? If you increase the nitrogen Roman numeral 2 oxide, you would say it would shift to the left. What about happens if you decrease something? So it was at equilibrium, but now our stress is a decrease here. So now we are no longer at equilibrium. Right now we're out of balance. So if there was too much, we shifted away. But now we don't have enough. We will shift towards to make more. So now that we know the reaction is going to shift to the left, everything the reaction arrow points to will go up. So that will go up. These things are on the other side of the arrow, so they will go down. Okay? Let's try one more. Decrease of water. Okay, originally it was at equilibrium. Now we have a stress, and that's our decrease. Not enough, shift towards. So now my equilibrium has to shift towards what we've removed, which means everything on this side will go up, and everything on this side will go down. This is for concentrations. Too much, shift away. Not enough, shift towards. Temperature. So temperature is not an actual form of matter, it's a form of energy. So here's our heat or temperature. I'm going to increase that, but we can do the exact same procedure. We were at equilibrium, and now we're not. So with an increase of heat, we're going to have to shift away. Too much, shift away. So shift away from that. What happens to the nitrogen? It will increase. What happens to the hydrogen? It will increase. What happens to this? It will go down because we're shifting in the reverse. What about if you increase temperature on this side? So we were at equilibrium. But then if we increase on this side, too much, shift away. So let's decide the direction of the shift. All right, so which direction is going to shift? Too much, shift away. I can't figure out how to do that. So shift away from it. So now if you're shifting towards this, we're going to make more. The amount of this hydrogen iodide will increase. The hydrogen and the iodine gases will decrease. Okay? Let's try one where we decrease heat. Not enough, shift towards. Shifting towards, it was at equilibrium. I didn't include that step. So we're at equilibrium. We don't have enough. We shift towards, which means the ammonia goes up. These gases go down. Okay? So too much, shift away. Not enough, shift towards. Another one. Decrease in temperature, which means there's not enough, shift towards. This goes up. This goes up. This goes, oh, that does not, see, I was getting too fast. If we shift away from that, we're going to decrease over here. Okay? Now, pressure is a little bit different. First of all, you should know that pressure only applies to gases. So if you're not dealing with gases, pressure is not going to shift your equilibrium. And you also have to have different number of moles of reactants and products. Now, wait a second. It's been a long time since we talked about moles. So coming back here, how do I figure out number of moles? Do we need to calculate GFM? Do I need to use 22.4 liters? No. All you have to do is count the coefficients. The coefficient of something not written is a 1. This would be a 1. So on this side, 2 moles. On this side, 2 moles. So even though we are gases, that we have the same number of moles on both sides means that pressure would not be an equilibrium stressor. But if you look at this one, for example, we have gases, but check out number of moles. This side is 1 and 3, total of 4 moles. This side is 2. So pressure would be a stressor on a reaction such as this, which is called the Haber process, which is what I'm guessing I included here in a minute. So here's the rule. If these are both met, this is how you figure out the equilibrium shift. If pressure is increasing, equilibrium will shift from the side that has more moles to fewer. If you increase pressure, think about it. Increase pressure. The side with more moles is going to have more collisions, which means we're going to go from high concentration to low. So increase pressure, more moles to fewer. If you decrease pressure, your equilibrium is going to shift from fewer to more. Unfortunately, that's just something you need to memorize. There's no reference table for that. But that only affects if you've got these two other conditions met, gas phase and unequal number of moles. So like I thought, I have the Haber process. I'm a one-trick pony here. So let's make sure that we have the conditions met to see if there would be a change for pressure. Magenta. First of all, we have the gas phase, which means pressure could be a factor here. The last thing we need to check is number of moles, which we already did. Let's do it again. There's nothing written here. The coefficient is 1, and there's a coefficient of 3. So on this side, we have a total of 4 moles. On this side, the coefficient is 2, which we have a total of 2 moles. So an increase of pressure would be a shift to the right, which means N2, if you're shifting this way, N2 will go down, H2 will go down, ammonia will go up. If you decrease pressure, we're going to go from the side for fewer to more, which means it would go to the left, which means these two things would go up and ammonia would go down. And if you wanted to include heat, if you shift towards, the heat would go up. If you shift away, the heat would go down. What will a catalyst do on equilibrium? Let's remind ourselves what a catalyst does. This is a definition that I seem to know right off the top of my head because the Regents loves it. A catalyst provides an alternate reaction pathway and lowers the activation energy. Okay? It also does not participate in the reaction. So it doesn't change products and it doesn't change reactants. So if it's not going to change any of those things, what's going to happen at equilibrium? It just means you're going to get to equilibrium faster. It's going to increase the rate of both the forward and the reverse. Okay? So it's not going to shift one way and then only adjust certain things. It's going to increase both. Look at that. Okay? All right, that's it for our notes. If you have any questions, please reach out. Take care.